This is a video from section 5.2. We're going to look at theorem 4. It says if f is continuous on the closed interval a to b, then the integral from a to b of f of x dx is equal to the limit as n goes to infinity of the summation from I equal 1 to n of f of x sub I delta x. And this is where delta x is equal to b minus a over n. And x sub I is equal to a plus I delta x. Okay? So it's a way that we're going to sum these rectangles and let n go to infinity. So x sub I is determining the height of the rectangle. All right? Now, use the form of the definition of the integral given in Theorem 4 to evaluate the integral. So we're going to look at example 1 where it says the integral from 0 to 3 of x squared dx. So my function f of x is x squared. A represents the lower limit. So in this case, a is 0 and b is 3. Delta x is b minus a over n. Okay? So we're partitioning the interval. And so in this case, it's 3 minus 0 over n, which is 3 over n. X sub I is a, which is 0, plus I delta x, which is 3i over n. And I'm going to basically take that information and plug it in. So we're looking at the limit as n goes to infinity of the summation from I equal 1 to n of f of x sub I delta x. So remember that x sub I, okay, is 3i over n. And so I'm going to get the limit as n goes to infinity of 3i over n quantity squared times 3 over n. But 3 squared is equal to 9, and 9 times 3 is 27. So we're going to look at the limit as n goes to infinity of the summation from I equal 1 to n of 27i squared over n cubed. Now, here's what we want to be looking at. We're summing on the I, okay, which means that 27 over n cubed is behaving like a constant, and that allows us to pull it out in front of the sum. And so this is the limit as n goes to infinity of 27 over n cubed times the summation from I equal 1 to n of I squared. But as I mentioned off to the side, the summation from I equal 1 of I squared is n times n plus 1 times 2n plus 1 over 6. And your instructor will probably want you to know that. All right? And so I'm going to replace this sum with this. And so I get the limit as n goes to infinity of 27 over n cubed times n plus 1 times 2n plus 1 over 6. And so I rewrote it up here. And so I multiply n plus 1 times 2n plus 1 first. And this is what I get. I get 27 times the quantity 2n cubed plus 3n squared plus n over 6n cubed. And then I distribute the 27 in, and I get the limit as n goes to infinity of 54n cubed plus 81n squared plus 27n over 6n cubed. But notice how we have matching degrees. And so when n gets large, you're just looking at the ratio of those coefficients. So I end up with 54 over 6. And 54 over 6 is 9, and that would be the answer to the first question. In example 2, so a little bit harder problem, we're going to take the integral from 1 to 5 of 3x squared plus 7x dx. So I call this like the brute force method. F of x is equal to 3x squared plus 7x. That's what we're integrating. That's this. The lower limit is 1, the upper limit is 5, and delta x is b minus a over n, which in this case is 5 minus 1 over n, which is equal to 4 over n. x sub I is 1, that's the lower limit, plus I delta x. But delta x is 4 over n, so x sub I is 1 plus 4i over n. And I'm plugging 1 plus 4i over n in for x. And you can see this is what I get. I get the limit as n goes to infinity of the summation from I equal 1 to n of 3 times 1 plus 4i over n squared plus 7 times 1 plus 4i over n times that quantity times 4 over n. And so that's the limit as n goes to infinity. So I did a little algebra in, so, like how I get 10, I take 3 times 1 and 7 times 1 and add them up. That's where I'm getting the 10. And then, for example, if I take 1 times 4i over n and double it, I get 8i over n. And then 8 times 3 is 24. 24 plus 28 is 52. So I'm going to get 52i over n. Make sure you're convinced of where I'm getting these numbers from, okay? And then, so I get 10 plus 52i over n plus 48i squared over n squared, and I'm going to take that quantity times delta x, which is 4 over n. So that's that last line. And so to get from here to here is a little bit of algebra. You got to square out 1 plus 4i over n, distribute the 7 in, distribute the 3 in, and combine like terms. Okay, so the next page. And so I broke up that sum, and so I get the summation from I equal 1 to n of 40 over n, plus the summation from I equal 1 to n of 208i over n squared, plus the summation from I equal 1 to n of 192i squared over n cubed. And so now 40 over n is basically constant. And so you're taking 40 over n times essentially 1 plus 1 plus 1 n times. So there's n copies of 1 because 1 is a constant. And so you should come up with 40 over n times n. So basically 40 over n times that upper value. And then I pull 208 over n squared out in front of the sum, and I'm going from I equal 1 to n of I, and then I pull the 192 over n cubed out in front of the sum, and I get the summation from I equal 1 to n of I squared. And so the summation from I equal 1 to n of I is n times n plus 1 over 2. And the summation from I equal 1 to n of I squared is n times n plus 1 times 2n plus 1 over 6. And so that's where I'm getting this third line here. And then I'm going to close that off here. And so I rearrange a little bit. I distribute the 208n inside. And so I get the limit as n goes to infinity of 40 because the n's cancel, plus 208n squared plus 208n over 2n squared, plus 192 over 6. And then, again, I multiply this numerator out. And if you notice, the numerator turns into 2n cubed plus 3n squared plus n. And then the denominator is n cubed. So again, I have 192 over 6 times 2n cubed plus 3n squared plus n over n cubed. And notice how the degrees match. And so when n goes to infinity, I should just be left with 2. When n goes to infinity over here, since the degrees match, I should be left with 208 over 2. And then I have the 40. And so that's exactly what I have. So remember, 208 over 2 is equal to 104. And that's where I'm getting that second one. And then again, it's 192 over 6 times 2 because of the matching degrees. That's what this is from. And so I get 144 plus 64. And so the answer to this example is 208. Let's take a look at example 3, and we're going to look at the integral from 0 to 2 of 2x minus x cubed dx. So again, this is the limit as n goes to infinity of the summation from I equal 1 to n of f of xi delta x. And so remember, f of x is the integrand. That's that stuff I'm integrating. My lower limit is a equals 0. My upper limit is b equal 2. Your delta x is b minus a over n, which is 2 over n. They're the same thing, okay? Now, x sub I is a plus I delta x, which is 2i over n. Remember, a is 0. And so I'm going to plug all that information in. So I'm replacing x with 2i over n. So I'm going to take the limit as n goes to infinity of the summation from I equal 1 to n of 2 times 2i over n minus the quantity 2i over n cubed, and then I'm going to multiply by 2 over n. And then I'm going to distribute in, and I'm going to get the summation. The limit as n goes to infinity of the summation from I equal 1 to n of 8i over n squared minus 16i cubed over n to the fourth. You know, and remember, if I take 2 to the third power, I get 8, and 8 times 2 is 16. That's where I'm getting that 16 from. Does that make sense? So I'm going to take 2i over n cubed times 2 over n, which is 8i cubed over n cubed times 2 over n. N cubed times n is n to the fourth, and then 8 times 2 is 16, so I get 16i cubed over n to the fourth. And so I break up that sum accordingly. And remember that the summation from I equal 1 to n of I cubed is n times n plus 1 over 2 quantity squared. So I'm going to put that as a note here. And that's what I did down here. And also, the summation from I equal 1 to n of I is n times n plus 1 over 2. And so this 8 over n squared is behaving like quote-unquote a constant. And same with 16 over n to the fourth. So remember, the index is I. All right, that's the hard part. And so I do a little algebra. So over here, I'm going to distribute the n in. In fact, I distributed 8n in. And I get the limit as n goes to infinity of 8n squared plus 8n over 2 minus. Now, I get 16 times n squared plus n to the second divided by 4n to the fourth. And if you notice on the next page, I multiply all that out, and I get the limit as n goes to infinity of 8n squared plus 8n over 2n squared minus 16n to the fourth plus 32n cubed plus 16n squared over 4n to the fourth. So I just squared that out, and then I multiplied by 16. And that's where I'm getting that numerator from. And so over here, 16 divided by 4 is 4. And so I get 4 minus 4, and then so the answer is 0. And that's how you do example 3. Now, let's look at these directions. Express the limit as a definite integral on the given intervals, so we don't have to evaluate. Now, here we have the limit as n goes to infinity of the summation from I equal 1 to n of e to the xi divided by 1 plus xi delta x. Now, for lack of a better term, my delta x is going to become dx. And this is the function that I'm going to be managing, okay? And so I'm going to get e to the x divided by 1 plus x. Now, I'm going to integrate. My lower limit is going to be 0. So I'm going to integrate from 0 My upper limit is 1, so I'm going to integrate from 0 to 1. That's it. So, this value before the delta x gives me my function. Delta x becomes my dx, and then I'm just integrating from 0 to 1. So if we look at example 5, notice how my lower limit is 2, my upper limit is 7. So I'm going to go from 2 to 7. And then this is giving me my function. So I'm going to go 5. So instead of xi star cubed, and xi star is just basically a sample point, a sample number, a sample value, okay? So I'm going to go 5x cubed minus 4x. The delta x becomes dx. That's it. Okay? And we'll do one more. So if we take a look at this one, we have the summation. Let me write that a little clearer here. So we have the summation from I equal 1 to n of x sub I star over x sub I star squared plus 4 delta x. And then my interval is from 1 to 3. So if I want to express this as an integral, my lower limit is 1, so I'm going to put a 1 there. My upper limit is 3, so I'm going to put a 3 up here. This is giving me my function. And so it's going to be x over x squared plus 4. Delta x becomes dx. That's it. And that'll conclude this video for section 5.2. And we did 3 examples of evaluating an integral using a Riemann sum, and then 3 examples of expressing a Riemann sum as a definite integral. So, all right, thank you.